Hi everyone. In this video, we'll be discussing power series. In particular, we will explore series which involve variable terms. We will determine for what values of a given variable that series converges, and we will define power series and learn shortcuts for determining for which values of the variable they converge. So let's start by looking at sort of a motivating example. So imagine that you were asked to consider the series, the sum n equals 0 to infinity, x to the n divided by 2 to the n. Now, just looking at this series, you now have a variable x, which is not like the variable n, which is indexing our sum, right? Now, this is just a different variable x. If I were to ask you, does the series converge when x is equal to 1? Well, now you have a value for 1. You could take this series, you could substitute in x is equal to 1, and you would get the series n equals 0 to infinity, 1 to the n over 2 to the n, which you may recognize is just the geometric series 1/2 to the n. Because this is a geometric series, we know that this converges, since the absolute value of 1/2, which is 1/2, is less than 1. Okay, so of course the answer here then will be yes, right? We can determine that the series does converge when x is equal to 1. Now, of course, we could change this problem up a bit. So what if instead of at 1, I ask you, does this series converge when x is equal to -3? Well, again, you can take this series, you can plug in x is equal to -3 in a very similar fashion to before. This will become -3/2 to the n. This is a geometric series, of course, and so now looking at this, if I look at the absolute value of -3/2, that's 3/2, that's now greater than 1, and so this geometric series diverges. So no, right? This series does not converge when x is equal to -3. Okay. So for any x value I give you, you sort of realize you can sort of play this game, right? For any x value I give you, you could plug it in, and then you just have a normal series, and you could use the fact that this series is a geometric series to determine whether it converges or diverges. But now, what if I just sort of wanted to answer the question all at once, right? I've seen already that, well, for some values of x, I get convergence. For example, x is equal to 1. For some other values of x, I get divergence. For example, when x is equal to -3. So what if I just ask, well, for what values of x does this series converge? Well, again, if I look at this series, this is really just x over 2 to the n. Okay. And I know this for any fixed value of x, right? This is a geometric series. And so I know that this will converge if the absolute value of x divided by 2 is strictly less than 1. Well, if I look at this inequality, that's really saying the same thing as the absolute value of x is less than 2. And that's really saying the same thing as x is between -2 and 2. Okay? And so we realize, right, that this will converge for all x values between -2 and 2. And in fact, it will diverge for all other x values, right? So we've already seen that when x is -3, which is outside of this range, we get divergence. But now we've sort of managed to totally answer the question of when this series converges or diverges. Now, if you give me any x value, I don't need to go do some test. I can just look and see, is it inside this range? If so, it converges. If it's not inside this range, then it diverges. So you sort of realize that you can do this sort of analysis of series which involve variables, right? And so instead of sort of looking at a fixed series which has no variables in it and asking, does it converge or diverge, we can now look at this new type of series, which does include a variable, and we can determine for what values of that variable the series will converge or diverge. So then what we want to do is we first want to define, so what are these series that involve variables? They're what we're going to call power series. So a power series about some value x is equal to a is an infinite series whose terms are constants times powers of x minus a. So what does this look like? Right? So this looks like some constant c0 plus another constant c1 times x minus a plus some other constant c2 times x minus a squared plus another constant times x minus a cubed, so on and so on and so on, plus a constant times x minus a to the n, again, so on and so on. Okay. Now, using series notation, right, we can write this as the sum n equals 0 to infinity of some constant times x minus a to some power. Now, in general, right, we notice that these constants Cn can depend on n, right? So in the previous example, right, when we were looking at the sum x to the n over 2 to the n, right, I can really think of that as 1 over 2 to the n times x minus 0 to the n, right? So my CNs in this case were 1 over 2 to the n, and this was a power series about the point x is equal to 0. So the 0 here is like our a. Now, the way to sort of think about power series is that they are sort of an extension of polynomials, right? So this is essentially like a polynomial, right? Constant plus constant times x to the first power plus constant times x to the second power plus so on and so on. Okay, so it's like a polynomial, but polynomials have some highest degree. These are infinite series, and so it's like a polynomial of infinite degree in some sense. So it's really an extension of the notion of a polynomial to an infinite series. Now, again, one of the key questions we're going to want to answer for these power series is, well, for what values of x do these series even converge? So let's look at another example. So imagine I give you the power series, the sum 5 times x minus 2 to the n divided by 3 to the n. Okay, so now again, we may first sort of want to rewrite this, right? This is the sum. And again, I'll just remind you, should really be a sum n equals 0 to infinity because we're writing the same thing over and over again. We're just going to leave those off. And additionally, convergence or divergence doesn't depend on your starting value here. So it's sort of unnecessary to specify every time exactly what these are. So I could rewrite this as the sum 5 over 3 to the n times x minus 2 to the n. So again, you'll see here, these are like your CNs, and this 2 is like your A. And now again here, I could play a very similar game as before, right? So if I were to look at this series, though, I could take in either form, I could take it back to an equivalent form that looks like this. Okay. And I could recognize that for any fixed value of x, this is in fact a geometric series. So since this is a geometric series, right, I have a times r to the n, okay, I know that this will converge if my r is strictly less than 1 and will diverge otherwise. So again here, this is really the same. If I multiply both sides by 3, this is really the same as saying the absolute value of x minus 2 is less than 3. That's the same as saying x minus 2 is between -3 and 3, right? Anytime you have absolute value of something is less than some positive number, then that means that the quantity inside the absolute values has to be between negative that number and positive that number. And now that I've gotten the absolute values removed, I can now add 2 everywhere. And I determine that this series will converge when x is between -1 and 5. Why? Because I've shown that -1 and 5 are the x values, or sorry, the range of values strictly between -1 and 5 are the x values that will make my r in this geometric series less than 1. So before we move on, let's pause for a quick knowledge check. I want you to determine for what values of x the power series below converges. So here we have the sum k equals 0 to infinity, 3 to the k times x minus 1 to the k. Okay, great. Let's take a look and see how you did. So if we're looking at this series, we can first recognize that we could rewrite this as 3 times x minus 1, whole thing to the k. So again, this is now a geometric series. For any fixed value of x, this is a geometric series. And this is my r. So this will converge if the absolute value of 3 times x minus 1 is less than 1. So here, again, the 3 is positive, so we can pull that out of the absolute values. We'll divide both sides by 3. Now, I have absolute value of something is less than 1/3. That means that thing is between -1/3 and 1/3. And now I can simply add 1 everywhere, 1 being the same as 3/3. And that will give me 2/3 is less than x is less than 4/3. So here I have the range of x values for which this power series will converge. Now, so far, these may feel fairly straightforward, right? You're looking at these series, you're essentially turning them into geometric series, but now the question of whether that r is less than 1 involves a variable, and so we have to solve some inequality involving that variable. But what if it's not a geometric power series? Okay, so what if we have a power series that looks something like this? So what if we had the sum n equals 0 to infinity of x minus 1 to the n divided by n factorial. So now note that there's no way to rewrite this in a form that's like the sum a times r to the n, right? This factorial term is sort of throwing off what we might normally do. Okay. Well, let's think about it then, right? So imagine x is some fixed value, and maybe if you want to think like, imagine x is 2, right? So 2 is really nice because 2 minus 1 would be 1, 1 to the n would be just 1. So if we just for a second say, what about x is equal to 2? What happens there? Then we get the sum n equals 0 to infinity of 1 over n factorial. How would you determine whether or not this series converged or diverged? Well, you'd probably use the ratio test, right? You see a factorial there. The ratio test plays really well with factorials. I'd probably try the ratio test. Okay, so if I were going to do that, what would I need to do? I need to look at the limit as n goes to infinity of the ratio of the absolute value of the n plus first term to the absolute value of the nth term. So in this case, everything's positive here, so I don't really need to worry about the absolute values. This would be 1 over n plus 1 factorial divided by 1 over n factorial. And now that would be the limit as n goes to infinity of n factorial over n plus 1 factorial. And that will simplify to 1 over n plus 1. And now as n goes to infinity, this denominator is going to go to infinity. Top is fixed at 1. So this limit will be 0. And so we would say, well, when x is equal to 2, this value, this limit is less than 1. So the series converges by the ratio test. All right. But again, I don't want to have to check every x value, right? There are infinitely many of them. So how can I determine for which x values this will work? Okay. Well, what if I tried to do this same thing, but I just left the variable x in there? Okay, so backing up a step, right? So what if I came back to the beginning of this problem and just said, well, I'm going to try to use ratio test in sort of the same way, but I'm just going to leave the x in there. So let's see, if I were going to use ratio test on this, let's do a little simplification first. I need to look at the absolute value of the a sub n plus first term over the absolute value of a sub n. And now again, if I'm leaving x sort of as it is, this would be the absolute value of x minus 1 to the n plus 1 divided by n plus 1 factorial divided by absolute value of x minus 1 to the n over n factorial. Now notice in this case, I can't just drop the absolute values because I don't know about x minus 1. It could be positive if x is bigger than 1, but it could also be negative if x is less than 1. So I actually have to leave some of these absolute values on here, and I have to deal with them a little bit carefully. So the n plus 1 factorial and the n factorial, I know those are positive. And so I could rewrite this as x minus 1 in absolute values to the n plus first power divided by n plus 1 factorial over absolute value of x minus 1 to the n divided by n factorial. And now if I do a bit of algebra here, I'll get x minus 1 to the n plus 1 times an n factorial. And then I'll get a x minus 1 in absolute value to the n and an n plus 1 factorial here. Now I can do some cancellation here. So I've got a x minus 1 to the n plus 1 divided by x minus 1 to the n. That's just going to leave me with an x minus 1 in the numerator. And these two will cancel in such a way that I'll be left with the n plus 1 in the denominator. Okay. So at the end of the day, this entire ratio simplifies to this quantity. So now I ask myself, okay, well, then what is the limit as n goes to infinity of this ratio? Well, I now know simplified what that ratio is. It's x minus 1 to the, absolute value of x minus 1 divided by n plus 1. But notice that the x minus 1 piece, the limit is a limit as n goes to infinity. As far as the limit is concerned, this is a constant. So since that's a constant as far as the limit's concerned, I can pull that value out. And now notice that this limit is just 0. And so now you notice that, well, it actually doesn't matter what x is, right? Because I'm going to get absolute value of x minus 1 times 0. So no matter what x value I put in there, my limit will be 0. And so this converges by the ratio test for all values of x. So for this series, it doesn't matter what x you put in there, right? Put in any x you want, as large as you want, right? Put in 1,000,001, right? Then you're going to get 1,000,000 to the n divided by n factorial. That series converges, okay? Put in x is negative 53. You'll get negative 54 to the n divided by n factorial. That series converges. I now know that this series converges for any x value you want to plug in there. Okay. So even when these are not just geometric series, we can use this notion from the ratio test to help us determine when they converge and when they diverge. Now, let's think even more generally. Okay. So what if I have just a generic power series that's the sum n equals 0 to infinity of Cn times x minus a to the n. Okay. So what can I just say about this sort of general power series? Well, I could carry out exactly the same sort of argument, right? So if I think of this whole term sitting here as my an, right? It's the nth term of my series. I could apply the ratio test. So I'm first just going to calculate this ratio. All right, well, the n plus first term in absolute values will be Cn times x minus a to the n over, or sorry, this the n plus first term, divided by the nth term, which will just be Cn times x minus a to the n. Now, I have a product, I have absolute value of a product, so I can rewrite this. This is absolute value of Cn plus 1 times the absolute value of x minus a to the n plus 1 divided by Cn in absolute values times absolute value of x minus a to the n. Now, these first two terms, not knowing anything else about them, there's not much I can do. And so I just get absolute value of Cn plus 1 divided by absolute value of Cn. But again, here I can simplify just like before. I've got an x minus a to the n plus 1 divided by an x minus a to the n. N of these x minus a's will cancel out, and I'll just be left with 1 by itself. Okay. And so I'll get this. And so if I were going to apply the ratio test, then I would come over here and I would say, okay, well, let me take the limit as n goes to infinity of this ratio. Of course, we've simplified this a bit, and we now know that this ratio is, so this is the ratio of the coefficients in the power series, right? So this was the ratio of the terms, right? But that's equal to the limit of the ratio of the coefficients in the power series times x minus a. But again, this x minus a is a constant as far as n is concerned, so I can actually pull that out. And I get this. Okay. Now, what we want to do then are step through sort of some possibilities, right? Because now whether this converges or diverges is going to depend on what this limit is. Okay. So let's actually think through a couple options, and I'm going to sort of carefully walk through each of them, and we'll talk about them. So one possibility, one which we've already seen, is that this limit could be zero. Okay. If this limit is zero, then this whole thing will be zero regardless of what x is. Okay. So if this limit is zero, then your power series is going to converge for every value of x. Right? If this limit is zero, then this whole thing will be zero. If the ratio of the terms is less than zero, if the limit of the ratio of the terms is less than zero, the ratio test says the series converges. And it's going to be zero regardless of what x is. Okay, that's option number one. Option number two, well, what if this is infinite? Right? If this limit is infinity, then it doesn't matter what x is, well, except one special case, but in most cases, if this is infinity, right, then this is going to be infinite and the series is not going to converge, except for one very special x value. When x is equal to a, right, when x is equal to a, these terms will be zero. So when x is equal to a, this is actually just always zero. Okay. So when this limit is infinite, you get that the series diverges everywhere except at x is equal to a, where the series converges. Now, of course, if you go back over here, if x is equal to a, your series is just zero. And so since your series is just zero, of course, summing up an infinite number of zeros is just going to give you zero. Okay, so we should always expect convergence when x is equal to a, but when x is something other than a, that's really, where things can start going wrong. So if this limit is infinite, then it's only going to converge when x is equal to a. It's going to diverge everywhere else. Now, the final case, of course, is what happens if the limit is, say, some value L. Okay, so if the limit is L, let's write out what would happen if this limit was L, or sorry, actually, I'm going to call it, well, yeah, L is fine. I'll get this. And so then I would need to look and say, well, is this less than 1? Because if it's less than 1, I'm guaranteed convergence. So what we would get is an inequality that looks like this, which if we do a little manipulation of the inequality would give us this. So what we see here is that if you calculate this limit and you get some number L, which is not zero or not infinity, right, then you're going to get convergence at A, and you're going to get convergence for every x value within distance 1 over L from A. We call that this 1 over L the radius of convergence. It tells me how far I know I always converge at A. The radius of convergence tells me how far I can go away from A and still be guaranteed that my series converges. Okay. So let's go back. Let's sort of walk through all these cases one more time and understand how we can determine for what x values these power series converge. All right. So again here, if we're in the case where the limit of the ratio of the coefficients of the power series is infinite, then the series only converges when x is equal to a. And in that case, we say the radius of convergence is zero, right? Power series always converge at the point that they're centered at, right? So if it's at the power series is at x is equal to a, then it's going to converge at a. The question is, how far can I move from a and still get convergence? Well, if this limit is infinite, you can't move any distance away from a. It will diverge for every value other than a. If the limit is zero, then the series is going to converge for every x value, in which case we say the radius of convergence is infinite. So again, if this limit is zero, then this product is going to be 0 for every value of x. 0 is less than 1, so you get convergence by the ratio test. Now, the slightly trickier one, and I guess I used k here instead of L, but same idea. So if the limit of these terms is some fixed value k, where k is between 0 and infinity, then the series converges when the absolute value of x minus a is less than 1 over k, and diverges when x minus a is greater than 1 over k. So when you're within distance 1 over k from a, you're going to get convergence. When you're more than distance 1 over k, you're going to get divergence. In this case, we say the radius of convergence is 1 over k. Now, it's worth noting here that what it doesn't tell us about is what happens when you're right at the sort of borderline of the radius of convergence. So what happens when you're exactly at distance 1 over k? And in that case, what's actually happening is, so if this is equal to 1 over k and this is k, you're getting 1. And the ratio test is inconclusive when you get 1. So in that case, we have to go use some other type of test to determine whether the series converges or diverges. And we'll see that in an example. All right. So let's start by looking through a few examples. Okay. So let's start by looking at the sum n equals 0 to infinity of 2 to the n times x to the n divided by n factorial. Okay. Now, the key for looking at these now is going to be to examine the CNs, right? So in this case, right, this whole term here is my a sub n, but I now just want the coefficient piece, right? So I really just want the 2 to the n divided by n factorial, okay? So the first thing I'm going to do is I'm going to examine the limit as n goes to infinity of the absolute value of Cn plus 1 divided by absolute value of Cn. Now, to help me do that, I'm first just going to try and understand this ratio, right? What is this ratio right here? Okay. So if I look at that, well, my Cn, right, is just 2 to the n divided by n factorial, right? I'm ignoring the sort of x to the n piece. So it's 2 to the n over n factorial, and all of that is positive, so I can lose the absolute values. This piece then will be 2 to the n plus 1 divided by n plus 1 factorial. And now if I do a bit of algebra, and I'm gonna speed this up a bit. And hopefully by now you're getting used to the cancellation of factorials and powers. I will get that this ratio is 2 divided by n plus 1. Okay, so now if I want to understand this limit, then I'm going to look at the limit as n goes to infinity of 2 divided by n plus 1, which is equal to 0. Okay, now, what does that limit tell me? Now remember, we're not doing the ratio test directly anymore, right? We're dealing with a power series, and we're using this theorem about when power series converge. Okay, so since this limit is 0, since the limit as n goes to infinity of Cn plus 1 over Cn is equal to 0, our radius of convergence is infinite. Now this power series, right? This power series was centered, right, at x is equal to 0, because normally I think about these in the form x minus a to the n. Here I just have an x to the n, so the a must have been 0. Okay. And so my radius of convergence being infinite means I can go infinitely far away from 0, and I'm still guaranteed convergence. Okay, so this essentially then tells me that my series converges for all x values. So in the second piece, really what I'm doing is I'm interpreting the limit. Right? So I first calculate this limit, but then I need to make sure I interpret it appropriately for this power series, right? So since the limit is 0, our radius of convergence is infinite. That means it converges, the power series converges for all values of x. All right, let's look at another example to see what other sorts of things can happen. So here I'm going to take the sum n is equal to 1 to infinity of x minus 1 to the n divided by 3 to the n times n. Okay. So similarly to before, the first thing I'm going to do is I'm going to evaluate the limit. And again, because this is a power series, I'm looking at the ratio, the limit of the ratio of the coefficients of the power series. Okay. So first thing, let's just actually calculate that ratio. So in this case, I have my x minus 1 to the n. That's sort of my x piece that I ignore. My coefficient is going to be 1 over 3 to the n times n. Okay. I'm going to look at the limit as n goes to infinity of don't want to do the limit yet. Just want to look at the ratio of the coefficients. So Cn will just be 1 over 3 to the n times n. The Cn plus 1 will then be 1 over 3 to the n plus 1 times n plus 1. Now, doing a bit of algebraic simplification, I will get 3 in the denominator. I'll get an n plus 1 in the denominator, the n in the numerator. So now going back to the limit, right, because the whole point of this is to evaluate the limit, then the limit as n goes to infinity of the ratio of the coefficients is this limit. And if you look at this, you have a linear in both the numerator and denominator. If you were to sort of multiply this out, you get 3n plus 3. Okay, so this limit will be 1/3. Okay, all right, so now I've calculated the limit, right? And the next step then is to interpret the limit. So what? Since this limit is, in this case, I've got it equal to 1/3. So it's equal to some fixed value. I now know my radius of convergence then is 1 over 1/3 or 3. Now, what does that tell me? Well, if I go up here, right, and look at my series, this series was centered at x is equal to 1, x minus a, right? So my a is 1. So this was centered at x is equal to 1, okay? And so I'm going to get that this series converges if, now my radius of convergence is 3. I'm allowed to go distance 3 away from 1. So I could go as far up as 4, right? If I go up 3 from 1, or I could go down 3, which would take me to -2. Okay. But what this ratio test really doesn't tell me is what happens at the end points here, right? I know that it will converge for any x value between -2 and 4. I know that it will diverge for x values bigger than 4 and diverge for x values smaller than -2. But what this doesn't tell me is what happens at -2 and at 4. So what I'm going to have to do is I'm actually going to have to go back and examine those cases separately. Okay. So in this case, when my radius of convergence is some finite number, right, some finite positive number, then I have to also check the endpoints. Okay. So here there's going to be sort of a step 3, which is going to be to check the endpoints. I'm going to leave this bottom piece of our conclusion here so that we have our endpoints and we know what values we need to check. And here we're going to have a third step, which is to check the endpoints. Okay. So I'm first going to start by checking the lower one. So what happens if x is equal to -2? So let's just take -2 and plug it in here. Right? So if I plug in -2, oh, sorry, x is equal to. So I plug in x is equal to -2, I'm going to get a -3 to the n divided by 3 to the n times n. Now, if I look at this, let's see, I could rewrite that numerator. So I'm going to just take the terms here for a second. So I've got -3 to the n over 3 to the n times n. I could rewrite this as -1 times 3. And so that'd be -1 to the n times 3 to the n over 3 to the n times n. Then the 3 to the n's would cancel, and I'd be left with a -1 to the n over n. So this series then is really equal to -1 to the n over n. Now, if you look at this series, you might say, oh, that's an alternating series. I could do the alternating series test. Okay. The alternating series test, I would say, well, 1 over n is decreasing, and its limit is 0. Therefore, by the alternating series test, this converges. You may also recognize that this is the alternating harmonic series, which we already discussed converges via the alternating series test. But what I can say here is when x is equal to -2, I get this series, and this series converges. So I'll just say here converges by the alternating series test. Okay. So now I can come back over here and I can update this. I now know it converges not just when I'm greater than -2, but when I'm greater than or equal to -2. Okay, so that equal sign is coming from there. Okay. Now, let me also check what happens when x is equal to 4, right? I have 2 endpoints. I need to check both of them. Okay. Well, if x is equal to, sorry, not -4, +4. Okay. So if I plug in 4 to this series, I'll get 4 minus 1, that'll be 3. So I'll get 3 to the n divided by 3 to the n times n. That will be just the series 1 over n, which we've seen many times now. And we know, in fact, that this series diverges. So you could just say that's the harmonic series. I know the harmonic series diverges. But it's also a p series, right? And so here, this series we know diverges. You could say by the p-test. And so it does not converge here. So I'm not going to put an equal sign there. Okay. So now I know that these are exactly all of the x values where this series converges. And for any x value that's not included here, I now know it definitely diverges. Okay. So by checking the endpoints, I'm sort of able to, the radius of convergence gives me almost everything, but then I go back and check the endpoints. That tells me what happens at my endpoints and whether I get convergence or divergence. So again, sort of moral of this story, right? We first find the radius of convergence. That requires us to calculate some limit and interpret it appropriately to find the radius of convergence. That gives me an interval where I know that my series converges, but I'm still not really sure about the endpoints. So when my interval has endpoints, so that's anytime I get a limit of the ratio of coefficients that is some finite real number, positive real number, then I have to go back and check these endpoints and possibly correct them. Now, it could be that it still diverges at both endpoints. Could be that it converges at both endpoints. But you do have to go back and check each endpoint to determine whether it converges or diverges. All right, let's look at one more example together. Let's look here at the series sum n equals 0 to infinity of n factorial times x minus, or sorry, times x plus 3 to the n. Now, again, here we can see that this series is centered at, now this is looks a bit tricky. I'm used to, in the normal form, it's x minus a, right? So if I were to look at this, I could really think of this as x minus -3. And so my series is centered at -3. So first I want to evaluate the limit, then try to interpret it to get a radius of convergence. Depending on what happens there, I may need to check some endpoints. Okay, so let's start then by evaluating the limit. So first, what is that limit? Or sorry, what is that ratio? Okay. So my coefficients here, my nth coefficient is just n factorial. Well, that's always positive, so I can drop the absolute values. So this will be n plus 1 factorial. And this will actually just simplify to n plus 1. So now I really just need to take a limit as n goes to infinity of this ratio, which is just n plus 1, but that limit is infinite. Yeah. So now, how do I interpret that? So because I get infinity here, that means my radius of convergence is 0. And what does that mean? Well, that means that it converges only at x is equal to -3, and it doesn't converge anywhere else. Okay. So obviously, if I plug in -3 here, I'm going to get 0 to the n, which is always 0, and I'll just get a sum of a bunch of zeros, which is converges to 0. But if x is anything else, this series will diverge. There's no need to check endpoints here because, again, we don't really have an interval that we're converging, interval of x values for which this power series converges. It only converges at x is equal to -3, and we can just leave it at that. Now let's pause for a knowledge check. I want you to take a try determining for what values of x a power series converges. So consider the power series below. We have the sum k equals 0 to infinity of x plus 2 to the k divided by the square root of k plus 1. So we're going to pause for a minute, and I want you to determine for what values of x the power series converges. Okay, great. Let's give it a try together. Okay. So again, the first thing I'm going to need to do is I'm going to need to look at this limit of the ratio of the coefficients. Okay. And before I can do that, I'm first going to need to actually just find that ratio. Okay. So if I take my coefficients are 1 over square root of k plus 1. If I'm using n here, then my nth one will just be 1 over square root of n plus 1. My n plus first one then would be 1 over square root of n plus 1, or n plus 2. And so this will become square root of n plus 1 over square root of n plus 2. Or you could write that as square root of n plus 1 over n plus 2. All right, well, now I need the limit. Of square root of n plus 1 over n plus 2. Now, as n goes to infinity, if I look inside this square root, this term is going to go to 1, right? I have n plus 1 in the numerator, n plus 2 in the denominator. And so this is a rational expression, same highest powers, leading coefficients are both 1. So the inside here, this goes to 1, and then I'm taking a square root. So I get the square root of 1, but that's just 1. Okay. So what does this limit tell me? This tells me that my radius of convergence is 1 over 1, or 1. And so if I look back at this series, let's see, this series was centered at -2. Okay. And so I get that this converges if I'm within distance 1 of -2. So I could go down by 1. That would give me -3. Or I could go up by 1. That would give me -1. Okay. But now I have to go to sort of this third step. I need to actually check these endpoints because this test doesn't actually tell me what happens at -3 and what happens at -1. So let's go then and evaluate our series at those endpoints. So now let's see, when I take this series and I take x is equal to -3, when x is equal to -3, I'm going to get -1 to the k divided by the square root of k plus 1. Now, if I look at this is an alternating series. So if I look at 1 divided by the square root of k plus 1, this is decreasing, right? Each time I make k bigger, this whole thing gets smaller. So this is decreasing. And its limit, as k goes to infinity, of 1 over square root of k plus 1 is 0. And so this is an alternating series where the non-alternating part is decreasing and its limit as k goes to infinity is 0. So this converges by the alternating series test. So I can immediately come over here and update this. Right? I get convergence when that is equal to -3. Now I also need to check x is equal to -1. So if I were to come up here, say, and plug in x is equal to -1, if I plug in -1, I'm going to get 1 to the k, which is just 1. And I'm going to get the sum 1 over square root of k plus 1. Now, let's see. Just looking at this, I sort of think this is like 1 over square root of k. That would be 1 over k to the 1/2. That's a p-series, and that p-series diverges. So I think this diverges. The question now is just, how am I going to prove that? Either by comparison or by a limit comparison. Well, if I want to show it diverged by comparison, I would need to find something smaller that also diverged. So if I wanted to make this smaller, I could make the bottom bigger, okay? I can't, like, getting rid of the 1 actually is going to make the bottom smaller, which is going to make the whole thing bigger, which is not the way I want to go. I could just do limit comparison here. So by limit comparison to 1 over square root k, this series diverges. Now, I haven't done all the work yet to show that. Okay. If I wanted to show that, right, I would look at 1 over square root of k divided by 1 over square root of k plus 1, right? Look at the ratio of these two. In this case, when I take that limit, you then take a limit as k goes to infinity, I would get that limit as 1. The limit comparison test then tells me these series either both converge or both diverge. But I know this diverges because it's a p-series, and therefore this series must also diverge. So I don't need to add a equal sign there. I just simply get convergence when x is equal to -3, not at x is equal to -1. All right. Now that example concludes our discussion of power series, but I think you should be left with a fairly large question, which is sort of, why are we discussing power series, right? Like, these really, they look sort of just like series. I guess in a purely mathematical sense, right, there is something interesting to study here, trying to figure out sort of why or for what range of x values a power series converges. But that's really not very different than any of the other series. It turns out, as you'll see in the upcoming and final 2 videos of the semester, that what you'll see is that there are special types of power series which are incredibly useful, called Taylor series. So over the next 2 videos, we'll be talking about Taylor series, their uses and applications. And so we'll see a lot of this material about power series come back to be very useful in our discussion of Taylor series.